Test. That looks better. Audio. Do I have audio? Is there audio on the live stream?
It's probably not up yet.
Looking especially dark. Why is that? No, don't do anything with the camera.
It does that when the screen.
Oh, the screen is, yeah, the screen is super bright. Let's go to the PowerPoint. Yep, that'll work. And do we have people on the live stream? Can you talk to Melissa and see what she's got going? Does she need the link?
Yes.
Where did we stop? Somewhere in here, probably. Test. Do we have audio? How does the stream look, Melissa? My mic is.
Oh yeah, sure.
We got to get that fixed so that it's a permalink.
I looked into it yesterday. I knew that you could do it.
I think you can do it.
Okay.
You found that it was impossible to do, or?
I couldn't find that in YouTube settings to do it.
If you schedule live streams, it doesn't give you links to them.
You can't schedule. I didn't find how to schedule the time.
I thought when right before you started, it asked you, do you want to start this one now or later?
It does. You can schedule live streams, but I really don't think you can schedule the time.
Okay, are we live? And ready? Let's get a little bit better camera angle. That focus looks okay. I'm just going to zoom in just a skosh. And I think I might stick me over farther into the corner. Okay.
What is the light being flashing on the screen?
Yeah. That is because there's too much light on it, I think. We're getting flicker. Well, poo. That. Oh, what all is running here? Is this guy running too? That usually is caused by over brightness, or this light oscillating at the same frequency that light is. But that's okay. We'll have to live with it right now. Okay, hi guys. Welcome to Thursday. We're gonna make it through another week. Here, your exam is Monday, 6 p.m. for most people, and there'll be an alternate time. And we sent you out yesterday an exam equation sheet. So you have all the equations and constants you'll need for not just this exam, but for all the exams in Chem 1. So you can download it from the website as a PDF. I attached it to an announcement. The announcement was scheduled to go out, so maybe I'm lying. If it didn't go out yet, it will go out this morning, and you'll have that. Also in the announcement is explanation of the PRISM homework. I think you guys have started that already. So when you do assignment in B courses, it takes you to PRISM. And then when you submit 3 correct assessments in PRISM, you get credit in B courses, 2 points in B courses. In PRISM, if you cycle through all the possible assessments and you don't submit 3 correct, then it'll just reset and you can start again to try to get 3 correct. So you kind of have infinite choices, and you can infinite chances, and you can practice till you get 3 correct. PRISM is also brand new. You guys are the first people to use it. So although we're furiously working on content, the content mostly comes from us. It's going fast, and there's going to be some typos, some mistakes. We already found 2 homework questions that had the wrong answer. Thank you guys for pointing that out. And please point it out. In fact, we're going to incentivize you guys proofreading for us. So if you find a homework problem or some text that just appears incorrect, send us an email. If it's a homework problem, tell us the homework problem, the exact text of the homework problem, and what assignment you're working on. Tell us why you think it's wrong and what it should be. And if we agree with you, we'll of course change it, but we'll also award you an extra homework point. So you get 3 points in B courses for that assignment. So that's exciting and new. But let's get on with chemistry. We stopped last time talking about transitions in hydrogen and in 1-electron ions. So if you ionize helium, helium has 2 electrons and 2 protons. If you take 1 electron off, removing an electron is called ionization. You're left with helium plus, which just means it has 1 electron left. Ionization is shown here. We know now that if you promote electrons by absorbing electromagnetic radiation, you can go up in energy levels, and that's quantized energy levels, so specific wavelengths of light. If you absorb photons of very high energy, you can ionize the electron. That is, you can get the electron to completely leave the atom. You give it so much energy, it can break free of the positive attraction of the nucleus. So ionization is taking an electron off. We'll talk a lot about that after the exam next week. And we understand it in terms of the wave properties now. So the electrons around the nucleus behave like waves, and we kind of saw that they were behaving like waves before we even put them around a nucleus. We did diffraction experiments and saw electrons had wave-like properties. So we assumed when we did the electron around a nucleus problem, so kind of when you do the electron in a one-dimensional sense, we used wave functions to describe it. So we're just doing a different quantum mechanical problem where instead of the electron being bound in a box, the electron is bound by the potential energy from the nucleus. So the positive charge attracting the negative charge is keeping that electron, essentially setting boundaries for it. And whenever we put boundaries on a wave property, set boundary conditions, then quantization naturally arises. And many of you are going to see this, if you haven't already, many times in mathematics. This is straightforward mathematics, differential equations that have specific boundaries on them. There's a whole field of mathematics, boundary value problems, and those solutions are well known. So a spherical boundary value problem or a linear boundary value problem. You have a differential equation that describes the energy of the system, for instance. We would have a differential equation for the atom that describes the potential and kinetic energy of the electron. In fact, that differential equation is famous. It's called the Schrodinger equation. We're not going to write that down, but that differential equation solved the solutions to that boundary value problem. That differential equation are the wave functions that we're going to look at today. And I told you last time, those solutions, that differential equation was written down before we even knew what atoms were. So 1700s. Those differential equations were solved by the brilliant mathematicians of that age, and they didn't have a practical application because there was no such thing. It was all abstract. There was no such thing as waves in 3 dimensions like that. But you can just apply that centuries-old mathematics to an atom, and you get modern quantum mechanics. So it's interesting how science keeps coming back on itself, and it brings up a really fundamental problem. Not a problem, but a fundamental issue. I guess you could call it a philosophical issue. Why does that math so well describe the hydrogen atom? It doesn't really have to. We understand electrons behave like waves, but electrons are very mysterious things, and we're going to see more about that today. This quantum mechanical theory for the hydrogen atom predicts the energy levels of hydrogen exactly as far as we can tell. So in some theories in physics and chemistry, you have a mathematical theory, and you test your mathematical theory by how well it fits your measurements. When you use quantum mechanics to describe the hydrogen atom, every measurement is exactly, as far as to the exact precision we can get, is exactly what's predicted by the quantum mechanics. In fact, we kind of take the quantum mechanics as the real number now. So as science evolves, you get better and better instrumentation, and you can keep getting another decimal point out in your precision. Every time that happens, it's the number that quantum mechanics for hydrogen atom predicts. Remarkable. It's probably the best theory in science for its ability to predict nature. So it works very well. The question is, why does it work so well? Why does matter behave in a way that we can describe with simple mathematics? That's a philosophical question. Matter doesn't have to do that. It's our math, but it does. So one of those things that can keep you up at night if you think about it too hard. So don't do that. We'll go on and just say, oh, electrons are waves, so of course they follow wave equations. So we talked about this transition in particular. We just compared helium plus to hydrogen. So the difference is in the helium system, there's 2 positive charges. at the center of the in the nucleus. In hydrogen, there's 1 positive charge. So Z, the charge on the nucleus, is 2 for helium and 1 for hydrogen, and that changes the relative orders here. We know this order goes as Z squared over N squared times this constant R, the Rydberg constant. So the bigger Z, the lower the ground state. So the ordering turned out to just be coincidental because of the factor of 2 between the helium nucleus and the hydrogen nucleus, that the 1 and 2 energy levels of hydrogen have the same spacing as the 2 to 4 transition in helium. That means both hydrogen and helium have the potential to have the same absorption line. So interestingly, though, in order to get helium to have that absorption line, it can't start from its ground state. So it had to be an excited state already, an excite 2. And then you could excite it to state 4. In general, we exist, atoms exist in their ground state, the lowest energy state. And everything in nature tends to stay in its lowest possible energy state unless it's perturbed by something. Some people say that there's stability there, that's a stable state. And stability is a bad word to use. I don't use it very often. It's stable only in the sense of time. So over time, if you look at it a lot, you're likely to find it here. Stable doesn't have anything really to do with energy itself. And people mess those two things up. Stability just means it's there a lot. And it's there a lot because it's low energy. It takes energy to move it out of there. So those are the same. So we're going to talk now about the wave functions in more detail. So we've kind of been looking at the one-dimensional, just the energies, the straight energies, and we're drawing those lines, those energy levels. The shapes of the wave functions, that is how you would plot them out in space, we can talk about that as well. And the plots in space of the wave functions we're going to call orbitals. So you've probably heard that term before, atomic orbitals. And the hydrogen atom, we talk about in great detail because it's a good model for the rest of the elements on the periodic table. And here's another interesting thing that might keep you up at night. We can solve the hydrogen atom, the 2-particle system, 1 plus, 1 minus, exactly. That is, there's a closed mathematical solution. Once you add 1 more particle, a 3-particle system, there is not a closed mathematical solution. So mathematics doesn't have a way to get a 3-particle solution. And it seems silly that modern mathematics can do these 2 particles, but add 1 more and it can't be solved exactly. After hydrogen, we use approximations the rest of the way. And those approximations are based on hydrogen atoms. That's another fundamental thing of mathematics. It's called the three-body system. 2 bodies, the differential equations we can solve exactly. 3, we can't. We can solve them. We can write approximations that last for a long time, that predict them for quite a long time. But eventually, reality diverges from our mathematics. So 2-particle system we can do. We can solve it exactly, and we get these precise energies. We're going to start categorizing the wave functions by their quantum numbers. We saw when you go to more dimensions, you get more quantum numbers, essentially 1 quantum number for each dimension. And what we do is just catalog the wave functions by their set of quantum numbers. So if you have quantum number n and quantum number L, 1 and 0, now we have to add 1 more because it's 3 dimensions. We're going to add ML equals 0. So that's a set of 3 quantum numbers. So that's one of the wave functions. That's one wave function around the nucleus. One state, one mode, one wave function that one electron can have around the nucleus. And it has a mathematical plot. And the mathematical plot has spherical symmetry. And that's kind of pleasing because we expected that. We thought atoms would be little spheres, and in effect they are to a great extent. And the 1,0,0 orbital, its function is spherical. It's in 3 dimensions. It looks like a sphere, and that means it has a radius r that we can predict. And for all the thetas and phis that you wrap around, it'll have that same value of r. And you can move r out and back, and you would trace out a solid sphere. As you go farther away, the wave function tails off. So it's going out, but as r's get big, that function gets smaller. So what we often do is just say, well, let's pick one r that encapsulates most of the probability, most of the wave function. And we draw that as a sphere, and that's kind of why we draw it as a hazy sphere. We're just letting the probability drop off to some value and then say that'll be the radius we make for that sphere. One thing we do, the numbers start to get cumbersome. So we associate letters with the numbers. And in a sense, when you're learning it, that just makes it more confusing. So we associate the letter S with L value 0. So they're the same things. If I say 1, 0, 0, or if I say 1 S 0, that's the same thing. So values of L equals 0, we also give the designation S. And then we call these S orbitals. So this S orbital also happens to be spherical, so that's a good way to remember it. Its value of M sub L is 0. And we'll give some designations to M sub L as well. So we can go to n equal 2. And remember, L can have a range of numbers. So the biggest it can have is n minus 1. So if I write down L 0, that's one of the possible values of L. When n is 2, when n is 1, the biggest L can be is n minus 1, so the biggest you can get is 0. When L equals 2, when n equals 2, L can have all the integer values between 0 and n minus 1. So you count from 0 to n minus 1, and those are the values of L. So n equals 2, I'll have L equals 0, L equal 1. And 1 is n minus 2, so I have to stop. So 2 values of L. One of them is 0, so we call that S. And we can draw that orbital. Now, this orbital is also spherically symmetric. It's an S orbital, S-type orbital, L equals 0. The difference is it has a radial node. So we can see that radial node. Nodes are places where the wave function goes to 0. Wave function crosses 0 in that. And we saw that in the 2-dimensional wave function at crossing 0. We saw it in the 1-dimensional wave function where the wave function crosses 0. So there's a 0 crossing in the wave function in the 2s orbital. The number of nodes an orbital has is always the maximum value of L for that quantum level. So the best way to think of it is a orbital will always have n minus 1 total nodes. That's also the maximum value of L. this has L0, but since n is 2, the number of nodes is n minus 1. So this has 1 node, and it's a radial node. So that's the low energy states of hydrogen. 1s, the ground state, the lowest energy state. We know that because n equal 1 is the ground state. That's how we've done it for all our waves so far. We started at integer steps. The integer steps, 1 is the lowest integer that we use for n, so that's the lowest energy state. That's the ground state. So there's our radial node. So we can stay in quantum level 2 and talk about the other value of L. There's a question coming in.
There are a couple questions in the chat about why there are infinite energy levels, but you can also eject electrons.
Okay, so the question is, there are infinite energy levels, but you can eject electrons.
And are all ground states the same?
And are all ground states the same? So one question, I can write infinite energy levels, but still eject an electron. So that's a good question. Is an ejected electron in an energy state where n equals infinity? And I suppose you could think that. So practically, you can, that is from a purely mathematical sense, you can write wave functions for any n value you want. But the very, very high energy ones don't have physical significance in keeping the electron around the nucleus. So very high energy does go to what you would call n equal infinity, but n equal infinity we're going to define as ionized, as removed. In fact, any practically high n, the energy of that electron is higher than the attractive force between the two. And when you are higher than the attractive force between the two, then the boundary condition doesn't apply anymore. So the electron stops behaving like a standing wave because it has more kinetic energy than the potential energy that would hold it to the nucleus. So once I get to a certain energy that is more kinetic energy than the potential energy holding it here, then it breaks free, still behaves like a wave, but not a bound wave anymore. So it then can have any wavelength. It can have any energy. And that's the infinite energy ionized state. So the simple answer is you could do the mathematics and you could write n to infinity. But at some point, you get to an energy level where the energy of the electron in the physical system, so we're not talking about a purely mathematical system, we're talking about a physical system where there's not enough binding energy. So wave mechanics breaks down. It's not a standing wave anymore. What was the other question?
Are all ground states the same?
Another question is, are all ground states the same? That same is hard to define. I'm not sure what you mean by same.
Do you have the same energy?
Do all ground states have the same energy? No, we've already seen that. The ground state energy is z squared over n squared. So the energy of all the orbitals, all the states, goes as minus z squared over n squared. So if z is different, the ground state energy is different. It's lower, more negative. And that should make a little sense to you, because if I have +1 charge here, there's a strong attraction energy. If I have +2 charge here, then there's a higher attraction between those. And then as you get closer, the energy goes even lower. We said energy goes higher as we pull them apart because we have to put energy in. If there's a big attraction here, you're getting more, you're going lower and lower and lower and lower, faster and faster and faster, as because you have 2 attracting 1. So let's look more at the orbitals and quantum numbers. So we can have 2 values of L for n equal 2. We talked about 1 where L equals 0. When L equals 1, we give it the designation P, and no one knows why. This is all historical. S doesn't really stand for, well, S and P don't have physical shape meanings. They're historical things from the spectroscopy of early, in fact, even before quantum mechanics, that there was we knew about the energy spacings before we could explain it by quantum mechanics. And the S and Ps started to come from there, and they just stuck. For you guys, it's just something you got to memorize. And I know I try to ask you not to memorize anything, but you do have to memorize that L and P are going to be used together. L0 and S are going to be used together. And when L is 2, we're going to use a D. Those letter to number correlations, you just have to memorize. It's not that much to memorize. So what we're going to do here then is say, well, L is 1, but M sub L depended on L, just like N and L had that relationship. N, the values of L went up to n minus 1 in integer steps. The values of M sub L start at minus L and go to plus L in integer steps. So -1, 0, +1, 3 values of M sub L for a value of L 1. So that means 3 wave functions. Each set of quantum numbers, every time you put 3 together, that defines a wave function. That's how we count them. So that means there's a wave function for N2 L1 M sub L minus 1 and N2 L1 M sub L 0 and N2 L1 M sub L plus 1. So there's 3 wave functions with N2 L1 or 2P. There are 3 2P wave functions. And we draw them like this. Here's a PX and a PY. So we call them PX and PY. And now you can see we're kind of making a rough association between values of L now and letters, and they're kind of geometric associations. So 2px, we're saying that's one of the possible values of M sub L, and that tells us something about the rough orientation of the orbital in our XY coordinate system. So if we set an X, Y, and Z direction, we can just do that arbitrarily, then the 2px, the lobes, the wave function lobes, have a negative and positive orientation. So they go from positive to negative along the x-axis. Another value of M sub L, the values go from plus to minus. You have that 0 crossing on the xz plane. So it's along the y-axis, the probability, the wave function. And then we can write the third one as z. So 2px, 2py, 2pz, that's just 3 quantum numbers, n, l, and m sub l. And each of them, the M sub L, is giving you some orientation information. The N number was giving you an overall energy information. So all of these orbitals, and I'll call them orbitals, they're wave functions. All of these orbitals have the same energy. Energy is defined by N. So I kind of draw them the same level on the board. That could have just been for space reasons, but they have the same energy. They're called degenerate orbitals. What's different about them is their orientation in space. So a 2px along the x-axis, a 2py along the y-axis, a 2pz along the z-axis. They have an angular node in them. Now, n equals 2. So remember, the number of nodes is n minus 1. So every orbital with n equal 2 has one node in it. And we saw the 2s, it was radial. In the 2p, it's angular. Now, these angular nodes are these planes, and a node is where the wave function changes from plus to minus in sign. So that's why I've drawn green and red here. And the plane of the angular node is the point where the wave function is 0, goes from plus to minus. Anytime anything goes from plus to minus, at some point it had to cross 0, right? This is a wave function. So a way to think about that in kind of wave function terminology is if I kind of extend the y-axis out here. Let me see if I can be super clever and make it go behind the axis there. And then I plot the wave function along the y-axis only. So y-axis yz slice, then the wave function kind of looks like this. Negative here, goes through 0, positive here. So that's kind of what I'm talking about. When I look at these pictures that you see in your textbooks, and we're going to look at more, I'm looking at the probability distribution. So this green line is something like the wave function. The red and green spheres are something like psi squared. And I wrote y there because we were just along the y-axis. But of course, these are three-dimensional functions. This is y, this is psi of r, theta, and phi. And this is psi squared of r, theta, and phi. And of course, when you square the wave function, everything becomes positive. So this in green is the wave function. If I square it, then I get all positive values. So you're saying to yourself, well, if it's all positive values, why do I have that negative there? Well, this is the wave function squared. It has all positive values. We put the negative and the positive sign there to remind us that the wave function changed sign. The sign of the wave function in those regions does matter. And we'll see it matters later when we bring the wave functions together. And remember, when we bring wave functions together and add them, then they can add constructively or destructively. So, and they don't add by their probability, they add by their actual function. So we have to remember, even though we're drawing a probability, that the wave function is negative there. So we can do our constructive and destructive interference later. I know that's a lot to swallow. Let's look at them. I might be able to do this. Let's see. Just by doing that. That's a big fat lie. Let's Go. Okay. Here's a big viewer where you can see a little bit more what I'm talking about. I'm going to go to n equals 1, and I'm going to go to s L equals 0. And what this is a plot of is the square of the wave function. Actually, you could think of this as the actual wave function. So the actual wave function of 1s orbital, and it's spherically symmetric. And I can rotate it, I believe. I can grab and rotate, but it's not very interesting. You can see the axes rotating, but it's spherically symmetric, so it looks the same from every direction. So stop rotating. So let's look at one that has some we can differentiate. That's the only n equal 1 orbital. I don't know if you can see what I'm doing here, but I'm going to go to n equal 2. And now I go to n equal 2, and there we're showing the colors, plus and minus. And this animation is running, so it's showing the wave function oscillating, and it's showing it oscillating by the change of colors. So when this out here goes to red, it's negative. When it goes to blue, it's positive. Or maybe it's just going red or green, blue. Nope, here it's going to go to red. So red is the negative, and it's going to oscillate back to blue, and that is the oscillation of the wave functions. They are wave functions going back and forth, and so we're showing you the phase change in color rather than in that's how we show the node, where it's going from positive to negative. So we can again highlight the node. I don't know which color to use. They give you, I think there's a way to choose other colors. Because why do they give us such gross colors? They give us this kind of puke green and this, icky pepto pink. So, but there's a node there, and you can see that area is not changing color. That area is staying 0. And here we're oscillating in the center, plus, minus, and then it switches around so that as it oscillates, now this is minus. Oops, gotta go back to my pen. Hurry. This is minus, and this is plus. So let's look at a different one. So that's the 1s. This is the 2s, 1 radial node, n equal 2, L equals 0. What if I go to L equal 1? Now there is that 2-lobe orbital. And I want to stop it from rotating and just get it fixed. Stop that. How do I stop it from running around like that? I think if I stop there, that just stops the animation. I want it to stop rotating. There's Z. Now, what if I get my finger really close to the middle? There we go. So here are the axis orientations. So that looks like a PZ orbital. So that means one of the M sub L values. And you can see it is also oscillating from plus to minus. So we remind ourselves when we draw the pictures that it crosses 0. There's that angular node here. And this is a PZ. So if we show a Z slice, that's where the node is. Let's show an X slice and stop it from rotating. So here I've sliced along the ZY plane. So this is the x-axis coming out of the board. So it's coming out of the board. And if I look at the slice, so you can see I've taken a slice of the orbital. And that slice is along the, I can even draw it in there. I guess I can annotate. That slice is along the Z. That's the Z axis. And this is the Y axis. So coming up here is the X axis in this case. So you can see, I should draw that right in the middle. X, Z, and then Y coming out at you. And then if I flip it over, oops, I'm a pen. If I flip it, you can see those two lobes along the, in this case, Z axis. So that's a slice, and you can keep going. I could go to n equal 3. Now n equal 3 and L equals 0 is also a spherically symmetric orbital. Let me get rid of the, oh, I'm going to keep looking at a slice here. In this case, so you can see two nodes, and you know there have to be two nodes because n minus 1, n is 3, n minus 1 is 2. So there have to be two total nodes, and they are in here. There's a node there and a node there. And here I'm looking at a slice through the center of the wave function. If I get rid of the slice, and I look just from the outside, no slice, rotation doesn't do anything. It's invariant. It's a spherically symmetric orbital. And this is actually allowing me to penetrate through and see the entire orbital. So spherically symmetric, but two nodes. This is a 3s orbital, L equals 0. If I stop the animation, then it'll stop going from, it'll stop oscillating. And here it is frozen in space, frozen in time. So it's not oscillating. And you can see plus, minus, plus regions with nodes in between them. If I go to stay in L equal 3, but go to L equal 1, so a p type orbital. Goodness, stop, you're rotating so fast. You can see now an orbital that looks like a p, that is, it has these two lobes along, in this case, the Z axis, but it also has a radial node. So it has this angular node. There's a node here that's a plane. Angular nodes are planes. And a radial node here. But overall, it still has that kind of P shape. One big lobe on this side and one big lobe on that side, except this radial node is making each side oscillate back and forth. So it goes plus 0, minus, minus 0, plus. Looks like a giant 2p, except a radial node. So I can take now a slice. Oops, I gotta stop the pen. I can't slice. Take an X slice. And here is the slice. Oh, but it just rotates on me. Should practice more with my animation. Stop rotating. Seems like I should be able to touch it closer to the center and stop it from rotating. But I can't do that here. I'll just hold it with my finger. It's not rotating. So now I see just along one axis, I'm taking a slice, and that's what we plot on paper. Obviously, we can't draw in 3 dimensions. So we're just drawing a slice when we draw it on paper. But you can see the slice is one of the planes, the plane of the paper, if we were drawing it. Here's the other side of the paper. And I can rotate it this way, the paper this way as well. And that is what we draw on paper, a slice. We remind ourselves of the plus and minus sign. Here we're reminding ourselves with colors. So this is now what we would call, well, now it just stopped. How'd I get it? I don't know how to get it to stop rotating. Somehow I was able to do it. It's not this button, that just stops the animation. So now it's going to start turning from, you're going to see the phase, the sign of the wave function. So you can go up in D's, and D's start to get a little complicated. Here's one of them. So we had one of the d orbitals. There's going to be 5 d orbitals, and why is that? So now we're talking about here, this is one of the d's. We're talking about n equal 3. That means L can be 0, 1, or 2. It can have 2 total nodes, n minus 1. But there are these orbitals when L equals 2, M sub L can go from minus L, minus 2, minus 1, 0, 1, and 2. So there's 1, 2, 3, 4, 5 kinds, 5 flavors of 3 L equal 2 orbitals. We call them 3D. The designation 2, we give D. So 3D orbitals. They're degenerate. They're of the same energy. M sub L doesn't change the energy. D doesn't even change the energy. N is the only thing that changes the energy. So these are all of the same energy. You would plot them on a line. There's 5 different ones. Here's one here. And I'll just show you some of the other ones. So I will go with no slicing, so you can see the whole orbital. That's one value of M sub L. It's called the dz squared. So one of the values of M sub L is z squared. And in general, we use those designations a lot, z squared for M, one of the values of M sub L. There's not a one-to-one correspondence, though. There's 5 kinds. One of them is z squared in the d's. Here's the dxy. I will try to rotate it into a form with z straight up. There I go. There's z straight up. So here's how we would draw it on paper. We would draw it like, and then it's going to rotate on me. Stop rotating. So that's how we would draw it on paper, with z going straight up and these lobes in the xy plane. And if you look at another of the d orbitals. That's the xz. Here's the yz, and that just tells you what plane those orbitals lie in. And you can keep going. There's going to be dx squared minus y squared. That's another shape. And that's also looks like a plane. There we go. Looks like it exists in a plane with alternating lobes, plus to minus. If I can get it to stop, seems like if I held my finger on there for long enough, it stopped. Excellent. So now it's just going, now it's just oscillating with phase, blue to green or blue to red. So I can draw now the nodes. So I'm at n equals 3. So the total nodes are two total nodes. In this case, they're both angular. There's a node there in that plane and a node there in that plane. So two angular nodes in this case. Angular nodes are planes. Oh, that sounds a little confusing. We'll talk about that one more time. And one more d orbital. Did we get all of them? Oh, one more. dxy. So many of them look the same. The one that looked the most different is the dz squared. So let me bring the dz squared into view there. The dz squared also has two nodes, one radial, one angular. So you can see the radial node. Let me get a slice that we can see the radial node. There's the radial node. So you can see the radial node, and you can't see the other two lobes because I'm taking a slice. They're up and down. So if I go to the X slice, you can see that ring in the middle, and now the two lobes up and down. So this animation is on the website, so you can look at that and play with that. We do expect you to know the shapes and the labels of the orbitals. So xy, the xy and the z, the dx squared minus y squared, which corresponds to which. So let's go back here. There's our pictures. The values of n equal 3, L can be 0, 1, and 2. We were just looking at them. So we can have a 3s, a 3p, and a 3d. We have those three values because that's the three values of L. So this is L. I can draw it down here. This is L equal 1, 2, and 3, S, P, and D. And then among the S's, we have one orbital because M sub L can only be 0. Here we have 3, minus 1, 0, and 1, the three values of M sub L. Here there are 5, minus 2, minus 1, 0, 1, and 2. These are the values of M sub L. So in the principal quantum level 3, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 possible orbitals, all distinguished by individual sets of quantum numbers. So if I give you a set of 3 quantum numbers, that corresponds to a individual orbital. And we've been saying that the whole way through. So let me ask you this. For which orbital is the plot shown psi in green and psi squared in yellow versus phi, one of our coordinates. So remember, I'll draw them up here. Oops. Oh, I don't have to draw them up here. I think if we, can you start the poll here, Ryan? So now you'll have the frozen picture of this, and I can just go like that, and you can see the values of R, theta, and phi, or if you've plotted out the JPEGs, you can see those R values of phi. So I want to say, as phi changes, what orbital have I plotted out there? Go ahead and talk about that one amongst yourselves. And we'll just do one vote on this. This one's going to take some three-dimensional thought. Trying to orient an orbital and then trace phi around and see how it changes with phi. We can show you your screen with a set of 4 if you'd like, so we can look at the poll. Oh, I didn't hit enough buttons. I could join a discussion if you mute me because we don't have one mic, right? Melissa could just assign me a room. I won't go in this time. You can leave me unmuted, and we'll just see what's going on. I don't like that flickering. I also don't like that flickering of the screen, and I've seen it before, and I thought I could get rid of it. Oh, I don't like that at all. That's just really tenuous. No, don't move it now. You're fine. But I really would rather have it come out of that other computer. You do that simply because you want to run the iClicker there. Yeah, that would make me much less nervous. Okay. Am I muted or am I on? Yeah. Okay. You just heard Ryan and I talking about technical things on the computer. So take a vote if you haven't so far. There's about 80. Let's see if we can see if 100 people are watching with iClickers today. 93. It's Thursday, which is essentially Friday. So maybe 93 of you are all we're going to get. All right, Ryan, let's see what those 96 people are thinking. We have no idea. Kind of equally spread out. B is slightly more popular, but not overwhelmingly. I'm just going to talk this one through with you. So I'll take over the screen again from Ryan. So we're looking at this and we're saying we need a p orbital that varies with phi like this. That is, the value is going to be, do I still have audio? The value is going to be versus phi 0, then it's going to get high, then it's going to get lower, and then it's going to go to -1, and it's going to go to 0 again. And that's between 0 and 2 pi. And phi is an angle. So I've gone around once around a circle, going from 0 to 2 pi. So let's look at, in this case, the 2py, and start with phi here, starts along the positive x-axis, and then it rotates out a little bit. And if this is the 2py orbital, then when phi is 0, that is in the plane where the angular node is. So the value of the wave function is 0 along the x-axis. As phi rotates out, I will encounter the positive part of the wave function here. So by the time I get to phi equals pi over 2 or phi equals 90, I'm at the maximum positive point. So I've gone from 0 here when phi equals 0 to here pi over 2 in phi, and now I have a big positive number. And you can see as it continues to rotate around, it'll go back to 0 when phi is pi all the way around to 180. And then it'll go negative because we'll encounter the values of this negative orbital, and then back to 0. So that was a hard thought experiment, 3D thought experiment for you. So go over that again on your own or in your small groups and see if you can understand that. You really understand shapes if you can do that. Here's something much easier. Which has the most radial nodes? The 4f orbital, which we haven't drawn at all, a 3d orbital, or a 2s orbital? Go ahead. Let's just discuss this one as well. This time I'll try to join one of you. Okay, am I unmuted? I'm back. I muted myself there, so we're okay. So am I on live? Okay. So we're back live. We have 105 responses. Let's see what you're thinking after 105 responses. My, still spread out quite a bit. So let me give you my thinking on this. Actually, it was explained to me just a minute ago by Neha, and she gave me a thumbs up. So I'm psyched. So let's go back to my control of the screen. And we were asking which has the most radial nodes among these three kinds of orbitals, a 4f, and any one of the 4f's, a 3d or a 2s. So we can kind of do the math. The total nodes are n minus 1. So this guy has 3 total nodes because n minus 1 is 3. This has 2 total nodes, and that has 1 total node. So that might get you thinking that this is going to have the most radial nodes. But L tells you something. L is the number of angular nodes. L is a very simple thing. If L is 2, you have 2 angular nodes. If L is 1, you have 1 angular node. So the number of angular nodes is just L. I wonder if that's the next animation. Ah, it is. L is the number of angular nodes. So when L equals 0, we call that an S. So that has 0 angular nodes, 2 angular nodes for D's, 3 angular nodes for F. So those values of L tell you the number of angular nodes. So this guy we said had 3 total because of n minus 1, but F is 3, so they're all angular. So this guy doesn't have any radial nodes, all angular. 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 Yeah, you guys probably can't even read that. Here, n, I'll write it up here. 3, n minus 1 is 2, so there's 2 total nodes. D means L equals 2, so it has 2 angular nodes, but there are only 2 total. So if it has 2 angular nodes, then it has no radial nodes. Over for 2s, 1 total node, n minus 1, s is 0, so 0 angular, so it must be radial. So that 2s is the only orbital there with a radial node. Are we going to get the big yellow box? Big yellow box says 2s. The big yellow box is like Vanna White. Flip the box. It is answer C. Okay, so let's continue. We can summarize this now. We know now a lot about these quantum numbers, and here I'm going to write out all these orbitals by their designation and by their energy. And we know energy is only determined, as far as we know so far, by n. So I'm going to have the ground state n equal 1, the first excited state n equal 2, but in n equal 2 there are several different orbitals, 4 total orbitals with these different sets of quantum numbers. Every time I have a set of 3 quantum numbers, I define 1 orbital. There are 4 orbitals in the 2 energy level. Sometimes that's called the shell. Principal quantum level 2. Principal quantum level 3, I have many more combinations of n, l, and m sub l. So in the 3rd principal quantum level, I have the s orbital, 1 radial node. The p orbitals have 1 angular, 1 radial. 3 of those. The d orbitals, L equal 2, have a angular set of nodes, 2 angular nodes. So that's how that looks. Let's talk about angular node again, because we were trying to figure that out. So angular node, I take one of the angles, phi or theta, and I say any value of phi or theta has to be 0. So if I look at an angular node and I say, and I'll just draw here the z and the x axis. The angle phi is here. So I'm saying an angular node is all values of phi have wave function value 0. So all values of phi have 0. That means every single value of phi is 0, and that traces out this plane, this xz plane. I can't go out of that plane because that would change theta. But I can have any value in here of, oh, I said that wrong. Any value of phi in here, I trace around, and I have to have, coming out here, this value here, I have to have that theta fixed, and I have to have theta fixed, phi moving. So theta fixed and phi moving traces out that plane. I can have any value of r I want. I can have any value of phi I want, but I can't move theta. That traces out this plane. So that's why it's called an angular node. I fix one of the angles, theta or phi, and let the other 2 variables just be any value. And that ends up being a plane. We call it an angular node because one of our angles, phi or theta, is fixed. And then I take all the values of r and the other angle, and that traces out a plane. I could also fix a value of r and have a radial node and let phi and theta vary. There's one more kind of node there, but we'll talk about that. One more combination, we'll talk about that next time. So let's look at electrons now more in detail. Turns out we're going to pick up one more quantum number, and that quantum number is associated with a property of the electron itself. And we recognize, this was first recognized because you could take electrons and you could pass them through a magnetic field. And electrons are charged, so we would expect as they're moving, they behave in a magnetic field, just like our mass spectrometer. They'd be spread out. And if the electrons with their charge had any orientation, then you'd expect a distribution of impacts. The electrons could hit anywhere on this screen. That designation is saying something even simpler, that if the electron behaved like a little magnet, that this was a little south pole and this was a little north pole, then as it went through that field, this would be, the south would be attracted to the north would be attracted to the south, but they have all different kinds of orientations, so they would just spread out. It turns out that's not exactly what happens when you do this experiment. Instead, you get 2 spots. The electrons hit here and here. So it's as if they're still kind of behaving like magnets. It's still kind of behaving like this is a south pole and this is a north pole, but only specific orientations. One orientation south up, the other orientation north up and going down here. So just two orientations of a little magnetic field associated with the electron. That property is called spin, and it's called spin because it kind of behaves like if an electric field moves, it creates a magnetic field. And since an electron has an electric field, it has a charge. If it were spinning, if we're going around in a ring, for instance, or just spinning, it would have a magnetic field perpendicular to the direction, to the plane of the spinning. So if it were spinning in one direction, it would have a magnetic field this way. If we're spinning the other direction, it would have a magnetic field that way. And this looks like electrons can have two values of that spin, but up and down only, and not a spread of magnetic fields from their spin. So they're either spinning up or spinning down and nowhere in between. We call it spin historically. Electrons aren't spinning. If they were spinning, you could calculate. You can see how big their magnetic field interaction is. So about how strong the magnetic field is. So you can calculate how fast they must be spinning to go through there, or you can calculate that where the charge has to be on a ring. And if you do that, the size of the electron has to be bigger than the atom. So they're not spinning, but they have this property that looks like spin, and that's historical. And you can see why it would be historical. This experiment makes it look like a spinning charge. So the spin is quantized. It can either be up or down. We're going to keep calling it spin. So spin up particles end up there, spin down particles end up here. And we're going to give that, since it's quantized, up or down and no values in between. It's a quantized system, up and down. We're going to give that a quantum number, m sub s. And it'll just have values +1/2 and -1/2. So that's crucial to our explanation of systems that have more than one electron. So far we've only talked about one electron. We're going to add another one, and this is going to give us the ability to talk about several electrons, because we'll be able to give them, we'll be able to kind of distinguish between this electron and that electron by their spin. So that is our next quantum number. That means we have 4 total quantum numbers now. We have N, L, M sub L, and M sub S. So now each electron, if you plot out its possible wave functions, we're going to describe the wave functions by 4 quantum numbers. And I know you're kind of saying 4 quantum numbers. Didn't I say I had a quantum number for every dimension? So does that mean there's a 4th dimension? And in a sense, yeah, in a sense you could call it that. After the exam, maybe we'll play around with that and decide how that could be. For now, you could think of it maybe as time. That's a 4th dimension. But we'll talk about how that extra quantum number relates to space after the exam, because otherwise we'll really mess you up. I'll tell you, quantum mechanics is a mysterious thing. So far, you could at least kind of wrap your head around it, because you're saying, okay, electron behaves like a wave. I can solve wave functions. I can see these standing wave patterns. I kind of get that. We haven't talked too much about the mysterious properties of quantum mechanics. This one is one of the most mysterious. People are still arguing over this one. And we'll talk about some of those arguments because they're interesting after the exam. So we get to this famous principle now, the Pauli exclusion principle, that says no two electrons can have exactly the same set of quantum numbers. So now we're going to just divide up the electrons in the atom by a set of quantum numbers. You do 4 quantum numbers, that has to correspond to 1 electron, 1 wave function. Every other electron has to be in a different standing wave. That means 1 electron, 1 standing wave, 1 set of 4 quantum numbers. The other electrons all have different sets of quantum numbers. So 1 full set of 4 is only 1 electron. So we can also say, then, once you have 2 electrons and you have 2 wave functions, so here I've drawn 2 lines and I've drawn them at the same level. So this is like 2 orbitals. Say it could be 2 of the 2p orbitals, or a 2s and a 2p. The principal quantum level is the same. L could be anything. So that could be the 3d and the 3s. They're at the same quantum level, same energy level. But if there are 2 electrons now, the 2 electrons have to go in those orbitals, essentially. They have to define which wave function is active. So there's several ways to do it. You could do the electron up and down, so m sub s plus 1/2, m sub s minus 1/2. You could do them in separated by L and separated by m sub s. And you could separate them by L, but have the same epsilon s. So spin up in 2 different L's, spin up and down in 2 different L's, spin up and down with the same L. Those are your choices. And it turns out one of those choices is better than the others. And that's called Hund's rule. Hund's rule says if you're gonna have electrons and they have the same L and the same N, the lowest energy is if they have the same m sub s. They have the same spin. So we could call those parallel spins. So if I have electrons in multiple orbitals with the same L, they go in parallel spins, and we'll find we can get them both in the same orbital, the same L, with m sub s 1/2 and the other m sub s minus 1/2, but that's a higher energy situation than this one. So they do this first if they have the choice. That's called Hund's rule. Pauli won a Nobel Prize for this kind of explanation of no 2 electrons can have the same set of quantum numbers. He didn't just say that and they gave him a Nobel Prize. Yeah, this is cool how this came about. This idea, this has the same idea of that things can't occupy the same space at the same time. So it's an exclusion of physical things in space. You can't get things infinitely close together if they have this spin property. So that's why it's called Pauli exclusion. This guy is going to exclude this guy from the same space eventually. When they go in the same orbital, you can say, well, that's kind of the same space, but we really have an extra dimension there to work with. So they can go there because we really have 4 dimensions to work with. So that turns out to be possible. And that's one of the coolest things about quantum mechanics. These particles that have spin 1/2 have this magnetic property 1/2, spin number 1/2. There's a bunch of them. Protons have spin 1/2. That's another particle with spin 1/2. In general, they're called fermions. they have half integer spin, and it doesn't have to be just 1/2. It can be 1/2, 3/2, just half integer spin. If you have integer spin, you're called a boson. And this Pauli exclusion principle does not apply to bosons. So bosons can more or less occupy the same space if you can get them into their ground translational quantum level. So it's called a condensation. You're bringing things down to very cold, stopping their motion and getting everybody in the same translational quantum mode. And when that happens, matter overlaps. That's actually been done. It's called a Bose-Einstein condensation. If you have bosons, matter can exist in the same space at the same time. There's one of the weird things about quantum particles right there. Electrons dominate most matter. So if your matter electrons are preventing normal matter in general from doing that. So the Pauli exclusion principle is preventing normal matter from overlapping. So we'll stop there. In general, degenerate orbitals, same energy orbitals, you have parallel spins, doesn't apply to bosons. You're not responsible for that boson fermion thing. It's just cool. It could be good if you knew that electrons and protons were fermions. Someone might ask you that on the street. Maybe. Okay, we'll stop there. And any questions here at the last minute coming up on the chat? Oh, I lost hours anyway. It's Thursday. Okay, so most of you are released unless you're interested. If there are any general questions, I am technically in office hours, so fire away. None. Good. Because I'm tired. Everybody left already?
So everyone can take a moment to breathe. I'm sure the questions will come.
I'm going to hang out here for a little while if you guys have questions.
Tests on Monday, ask questions.
The test is on Monday, midterm exam 1.
Great opportunity to ask
We can babble on more about this mysterious fermion boson thing. I wonder if there's some good. On Tuesday, I'll talk about it a little more for everyone because there's some other cool stuff. No questions. Nobody on the chat. Is
in the live stream chat? I'll get back onto the Zoom and make sure there aren't any there. But
I am the explanation of no questions is either, I guess there's several. Maybe the live stream crashed. We think it's still running. Number 2, you understood all of that. Awesome. Number 3, let's see, maybe a meteor has struck and
oh my gosh,
we don't know it.
Melissa says there are questions and I am not seeing them.
Oh, Melissa says there are questions in the chat. So a third explanation is we can't see your questions for some reason. Maybe Melissa, can you relay the questions?
I'm gonna just log on to the live stream so I can see the questions as well.
Oh, okay. I'm sorry. Questions are coming in.
Right.
You were frustrated. We just couldn't see them. Okay, here they come. Ryan's gonna start firing them off.
Is one-dimensional quantum mechanics the last concept on the midterm, or will there be 3-dimensional?
The question is, what does the exam cover? The exam covers up to the last thing I said today. So up to the Pauli exclusion principle and Hund's rule.
What is a degenerate orbital?
The question is, what is a degenerate orbital? Those are the orbitals that hang out behind the 7-Eleven and smoke. the police come and get them, they call them degenerates. Okay. Degenerate just means equal energy. It's a simpler term than it sounds. So wherever I say degenerate, you can say of the same energy, and it will work.
Can you go back to the first chem quiz? There was some confusion on that.
Can I go back to the first chem quiz, or there looks like there's some questions about the first chem quiz of the day? I think I can.
Okay.
I mean, I know I can. I just don't remember which one it was. So let's go back to where we started today. We reviewed that one. Oh my gosh, it's this one. Yeah, that is where. Okay, so it's this chem quiz, and I agree. That is a little harder to understand. So let me go here where I have some room to write. So what we're doing here is along this axis, we're plotting the value of phi. Now, phi is the angle from the positive x-axis. So phi is an angle. Ooh, that's an interesting thing. I desperately want some new colors. Apparently I can't get new colors. So I'll use my Pepto pink color. If I have a vector here in the XY plane, the angle from the positive x-axis is phi. So phi can take on values here, 0. And as it swings around and gets to the y-axis, since it's the angle from the positive x, once it gets to the y, phi must be 90 degrees. And we know that that is also written pi over 2. And then as it continues to swing and gets around to the minus x-axis, and the value of phi here is 180 or pi, and so on. It'll go around here to the minus y-axis, and it'll have the value 270 degrees, or phi equals 3 pi over 2. And then when it gets back around to the x-axis, it's gone a 2 pi revolution. So the value is 2 pi or 0. So you have to say then, this lobe of the orbital is sticking out in space right here. It's a circle. It's a sphere, and it's sitting out here on the y-axis. So as soon as phi leaves the x-axis, where this node, the node is in the plane zx, there's 0 value of the wave function there. That's the planar or angular node. That is the node where the other angle, theta, is fixed. So phi comes around here. As soon as it leaves the x-axis, it encounters some of this y orbital. Then it encounters more of it, then more of it, then more of it, then the max of it there. So we could draw that a little like this. This comes out of away from the x-axis. It comes away from, this is coming out, away from the y-axis to sphere. So it's coming out from the y-axis in that direction, in x, it's also coming out from the y-axis in z. That's a sphere. So as soon as you go away from the x-axis with your phi, here's another value of phi, you start encountering the values of the wave function. So I'm encountering the values of the wave function there, and they go from a relatively small number out to the maximum they can be right there. So that's the, as I go from phi and I start getting bigger and bigger and bigger on phi, I get to the maximum total value of the wave function. The farthest it is away from the origin here, the farthest away from the origin is its maximum value, and it hits it when phi gets to the y-axis, and phi is 90 degrees. So that, oops, just erase some of the, oh, poopy, go back. So this value of phi, gone all the way around to there, phi is pi over 2 or 90 degrees. That is the maximum value of the wave function. And that maximum occurs right here at phi equals pi over 2. And as I keep going around with phi, I get to phi equals pi or 90 degrees. And now I've come back to this same plane, the xz plane. And in the xz plane, the wave function is 0. That's a node. So I come back to 0 here. The value of the wave function is 0 there when phi is pi. And then I keep going. And when I keep going, I start encountering negative values of the wave function. So I had positive values of the wave function here. I'm going to get negative values of the wave function here. So now I get the same negative values going around the circle. And then when I get back to 2 pi, I'm come all the way back to where I started, and I'm at 0 again. Okay, other questions?
How do you find L to determine angular nodes?
How do I find L? The question is, how do I find L to get angular nodes? L always comes in a range of values. So I think I can make this black. L comes in a range of values that depend on the value of n. And so L comes in a range of values depending on n. So you don't find a specific one per se. You just get a range. So when n is, say, 3, L, the biggest it can be, is n minus 1. That's the max. But it can be any integer value from 0 to that max. So in this case, n minus 1 is 2, but L can range from 0 to 2 in integer steps. So it can be 0, 1, and 2. So it has 3 possible values, but maybe what you're asking is, how do you get the value? The value comes, so we could cast this in terms of an exam question. I would say something like, and you've already seen it on the exam, what's the value of L if the orbital is 4f z squared minus y squared. Well, that's straightforward because we give these values of L letter designations as well. So when L is 0, we call that S. When L is 1, we call that P. When L is 2, we call that D. When L is 3, we call that F. So to get the value of L, or what is the value of L in this orbital, the value of L in that orbital is 3. That doesn't mean it's the only value of L in principal quantum level 4. There are also the values of 0, 1, 2, and 3, all those values, but each set of 3 define one orbital. So here I have N. Here I have, for this 4F, N. I can't seem to draw an N. For 4F, N is 4. That's easy. L, we just get from this formula thing that we have to memorize. L equals 3 means F. So L is 3. And then this little business down here would determine M sub L. But I'm not going to ever ask you that. I'm never going to ask you, is z squared minus y squared what value of M sub L that is? I won't even ask you for the simple ones, like 2px, 2py, 2pz, 3 values of M sub L, because there is no one-to-one correspondence. M sub L equal minus 1/2 is not pz, or in that case, it would be a little careful, but I'm not going to ask you that. So there's no correspondence. Is px, as far as we're concerned, px could be M sub L minus 1, 0, or 1. Could be any one of them. You can't translate an exact number there. And that has to do with interesting properties of the mathematics and quantum mechanics in general. It turns out we get to pick, when we're doing the mathematics, we get to pick these. And we pick them, and then we give them crazy designations. And turns out there's a lot more of these that can happen. And the ones that we pick are the combinations of them that are easy to draw. So, okay. Other things?
Can you talk about Hund's rule again?
Hund's rule, yes. So Hund's rule is the simplest of the rules, and I didn't make it obvious on that last slide. So Hund's rule. So am I going to write? Yes, we had Pauli. And that said, I can't have electrons with the same 4 quantum numbers. So if I have a choice among degenerate orbitals, and remember, degenerate just means equal energy. And so for our purposes so far, degenerate means N is the same for all those. So Pauli said that no 2 electrons can have all 4 quantum numbers the same. So the principal quantum level N, say here, is 4. And then let's say this L is 0, that L is 1, that L is 2, that L is 3. They're all degenerate. They're in principal quantum level 4. It can be any one of them, L. So that's 2 quantum numbers. Let's go one more. Let's go to what do we have? NL. Now we'll go to M sub L. M sub L is the values of L from minus L to plus L. So in this case, M sub L, since L is 0, can only be 0. Now we've got 3 quantum numbers, 4, 0, and 0. The last quantum number is M sub S, and that's what we're calling this spin property of electrons. And that can be plus 1/2 or minus 1/2. And I have to pick one of them, because if I'm talking about this orbital here, I can only have this set of quantum numbers once, 4, 0, 0, 1/2. I can have 4, 0, 0, minus 1/2. And we draw those as little arrows sometimes to remind us. Here's M sub S plus 1/2. Here is M sub S minus 1/2. So this picture tells you something about Pauli exclusion principle. I have an L, an M sub L, an N, an M sub S, and the other M sub S. That electron has 4 quantum numbers. That has 4 quantum numbers, and they're different. So that's Pauli. I got to have different ones. That means Pauli says, Pauli says I can't have this. That's both plus 1/2. So Pauli says none of that. How far back can I go? Cool. Pauli says that's okay. Hund says, well, if I can have that, what's the relationship between that, where the L's are the same, and this, where the L's are different, but the M sub L is the same? So Hund says, let's just give them a priority. So I can have this, let's just talk about these 2 values of L now, and say, which one is better? Is it this one that is all yellow, both up? Or is it better to have one up and or 2 up in the same orbital? Or is it better to have 1 up and 1 down? It turns out that up in degenerate orbitals is the lowest energy situation. So Hund just says that the winner of the 3 combinations, and let's just draw the 3 combinations again, get rid of everything. So the 3 combinations, when I have degenerate orbitals, the 3 possible combinations are 2 values of M sub S that are different, 2 values of M sub S that are the same but L is different, and 2 values of M sub S where L is different or m sub L. So what is the lowest energy option? And Hund says it's this one. One way to rationalize that is, if this really is a magnetic property, then magnets aligned next to each other is a more preferred state than them anti-parallel. So you could think of it that way. But all the electrons, they all go in parallel into degenerate orbitals until you run out of space, and then they will start pairing. So if I had 3 electrons, I would eventually put one there. But Hund says parallel until you run out of degenerate orbitals. Okay? Other things?
So this one's not from today, but for a wave-like particle in a bounded box, if you increase mass of the particle or length of the box, do you decrease energy?
The question is, it might be really cool. Hold on a second. Can I go? Oops. I'm going to try to go to, oops, not the camera. I'm going to go to Chromium. I just want to see what's open. One of these is the 2D square well. Can I change the, yes. Okay, so the question is, I got a particle in a box, one-dimensional box. Here is the second energy level. It's, I can probably get rid of the, well, first I'll go to the ground state. The ground state is the one wave. I will, I want to see the wave function and not, can I change? So here is the lowest energy state of the particle in the box. As I can go up in eigenstates, I can go from that one to the 2 nodes. I keep going up to more nodes, and I can keep going up until I get more and more and more nodes. That's the lowest energy. The question is, what if I change the mass or the width of the well? Well, this animation shows it dramatically. I can take the width and just change it. So notice if as I change the width of the well, what's happening to the energy spacings? The energy spacings are getting bigger. So now I go from here to the second state. Clear. It was a better one. There was a slightly better one, but I'm going to go back to the ground state here. So the energy levels have gotten bigger. The spacings have gotten bigger. So decreasing the size of the box, making L smaller, increases the energy spacing. So the energy transitions, delta E, are going to get bigger. So as you change the width of the box. Here I've made it narrower. And these energy level spacings are getting bigger. Here's the energy level spacing there. Here's an energy level spacing. Here's an energy level spacing. Ding, ding, ding. If I increase the size of the box, increase R. I hope you can see that, but I'll annotate on it again. Now, the energy spacings are very close together, and there are more of them. So that's how the energy profile changes with the size of the box. And if I change the particle mass, let's go, whoops. I'm going to go to a narrow box, so I have wide energy spacings. And if I change the particle mass, I'm going to go to larger mass. You can see those energy level spacings contract. So the energy of an individual level goes up with the particle mass. The energy of an individual state goes down with the width of the box. So for any arbitrary energy level E sub n, we saw that if the L gets bigger, L gets bigger, that E's get smaller. And we know that general form had an L squared on the bottom. Bigger L's, smaller E's. And we can also see, if we look at the squeezing one more time, if I go to bigger mass, the energies are of an individual level drop. So I have that n squared over L, n squared, L squared dropping, the m mass of the particle causing the energy levels to contract, energies to go down, and the length of the box causing the energy levels to go down. Okay? Is there anything else hanging out there?
ML has integer values, right?
M sub L has integer values, yes. The only half integer quantum number is M sub S. And there's only two of them, plus 1/2 and minus 1/2 for M sub S.
That is all. People said it made less sense. Any more before we go? I think that's all. It's 10. Oh.
This will help me maybe more later.
That's nice. Question.
Yes.
An orbital is described by 3 quantum numbers, NL and ML.
Yes, an orbital is described by 3 quantum numbers, n, l, and m sub l. The 4th quantum number, m sub s, is differentiates the electrons that can occupy that orbital. 1 spin up m sub s, 1 spin down m sub s minus 1/2, plus 1/2, minus 1/2. So you can think of an orbital as a region of space that can contain 2 electrons. The 3 values of n, l, and m sub l give you the region of space. M sub s plus and n sub s minus give you the 2 electrons that can be there.
All right. Those are all the questions that are coming up.
Okay, guys, good luck on Monday. Monday, this lecture will be a review. So no new material Monday. We'll review for the exam, so that'll give you a little bit of a break. Kind of a bummer, this coincides with a holiday weekend. I did not even realize that. We've just been our heads down trying to get this all together for you guys. I don't even know what day it is. You can see that Ryan has to tell me what day it is as we go. Okay, good luck. We'll see you on Monday.